to Taylor, I didn't went back.
So I want to clarify something I said, but to start off last time, we were talking about decision trees, right? Before we begin, any questions in Daytona Beach?
I think their microphone's off.
Okay, did I turn that off?
I think it automatically gets turned off when the session starts.
Okay, I just gave them. Okay, I do want to go back. Hello? Any questions in Florida?
It's off again.
It's on again. You're good? Okay. So I want to go back to the, it might have even been, because I was uploading the video and I noticed something that I hadn't made clear. Let me see if I can find. Where did I go through that example? It's towards the end. So I wanted to just go back and clarify one point that I made on the decision tree example. We ended up ignoring the ID code, but then we chose the outlook to split over, and then that splits it into the three branches. The sunny, overcast, and rainy. And then what I didn't make clear, I think I said you would then split over those. And what I mean is for each of those, so you follow the sunny branch. And then you would again, that's where you would recursively split over the other attributes, which are temperature, wind, and humidity. For each of those three branches, whether you're sunny, overcast, or rainy. I just wanted, because I went back and I noticed in the video that was unclear. So, is that clear, Jeremiah? You seem to be nodding your head yes.
I got it.
You got it?
Clear as a bagel.
Okay, so then what I'd like to do next is move on. So we talked pretty much the last couple times, we talked about decision trees. And then we discussed model overfitting. And this time we're going to continue with classification, but decision trees are not the only approach to classifying, and we're going to begin looking at some other approaches. The first one we'll look at is actually somewhat related to what we talked about before. They're called rule-based classifiers. We're also going to look, whether today or next time, at nearest neighbor classifiers, Bayesian classifiers, support vector machines. So we're kind of in the midst of analyzing numerous different algorithms, all for the purpose of classification. So rule-based classifiers, we'll go through an example, but the basic idea here is what we're searching for is a set of rules. So they're going to be of the form if-then. So if something and something and something, then we classify as a certain classification. Or if you have another rule of a similar sort, then you're going to classify as the same class or a different class. So you have a number of different rules, and each one will classify an instance as a particular class. So the approach we're going to take is a little bit different, and it's called a covering approach. And so if you remember how we looked at the decision trees, we started at a node, a root node, and again did some things recursively. We're still going to do some things recursively here. And then we would split, and it's called a top-down approach. In some ways, what we're going to be doing this time is going to be more of a bottom-up approach. We're actually going to look at the instances and the different classes that we end up with, and then try to come up with rules that cover each of those instances, while excluding instances not in that class. So I'm going to use this time, I'm going to use the different example instead of the weather example. This is an example called the contact lens example. I couldn't fit it onto one page, so I'll go back and forth sometimes between this page and the next one. But we've got our attributes age, prescription spectacle, prescription, astigmatism, and tear production rate. And the class that we're interested in obtaining is what type of lens to prescribe. Recommended ones would be soft, hard, or no lens, depending on the different attributes. And so the first, I think there's 24 instances, and so the first 12 are here, and then the next 12 are on this second page. So here's the example that I think will help us understand the difference between this approach and decision trees, although we end up with very similar outcomes. We're going to seek out, say, a rule for a particular recommendation. So all the instances of hard lenses as our decision. So we're going to end up with 9 choices, and I'm going to go back to the previous screens to explain exactly what I mean here. So we've got, if your age is young, so let's back up a couple slides here. So we've got 8 instances where the age is young. Of those, notice that we have exactly 2 on the right-hand column, and it's the 4th one and the 8th one, where the lenses are recommended to be hard lenses. Okay. So moving back forward, so 9 choices. Age equals young. If we were to use that as a rule, notice of the 8 young instances, 2 of those ended up giving a prescription of hard lenses. So on the right-hand column here, we have 2 out of 8 giving our desired class. If you went back to the prior screens as well, if you had a different age, pre-presbyopic, I'm not sure if I have the pronunciation, but 1 out of 8, 1 out of the age 8 instances there. And same for presbyopic. I think that second Y should be a T. But we also have, moving back, we have spectacle prescription. So if I go back to the spectacle prescription, we have, again, 8 instances here on the first page of myope, and another 4 on the second page. So that's a total of 12 spectacle prescriptions of the type myope and 12 of the hypermetrope. And of those, 3 of the 12 myope instances lead to a recommendation of hard contact lenses, whereas 1 of the 12 hypermetrope result in the same prescription. And similarly, if you go back and look at astigmatism, if you don't have astigmatism, you get 0 of 12 instances being recommended as hard contact lenses. But if you do have astigmatism, 4 out of 12. And similarly for your tear production rate. So before I continue, is it clear where those ratios, those fractions came from? As well as the whole setup so far. I see some heads shaking up and down. I don't see a hand on the screen from Daytona. So moving on, what we're going to do is we're going to look at those fractions, and we're going to look at the largest fraction. Similar to, in a way, what we did with the decision trees. 4 out of the 12 cases, or is the largest fraction that we obtain on the right-hand column. We have 2 choices there. If you end up with the same fraction, if you have more instances, we're going to want to choose that. But in this particular case, the 412 is the same as the 412 in terms of 12 instances. So at that point, it doesn't matter which one we choose. I'm going to choose, I think I chose the astigmatism being yes. So we selected the largest fraction, 4 out of 12, and in this case we had a tie, both in terms of the actual fraction, but also in terms of the number of instances. And so we just chose one at random. So we're going to start off with that as our current rule. Okay? So our current rule is just going to be very simple. If astigmatism is yes, then a recommendation is hard contact lenses. But our ultimate goal here, in a lot of these cases, and the particular algorithm we're going to go over, is going to be 100% classification. So in this case, we're going to desire a more accurate rule. So far, we've got only 4 instances out of 12 covered. We need to cover everything. Okay. So now we're going to look at the next term. We're beginning to kind of filter down into the process. So now we're going to just restrict ourselves to the set of instances. We had only 12 cases now. We're still under the setting, well, what was it? Astigmatism equals yes? Mm-hmm. So if we go back to our original case here, where's astigmatism? We have 6 cases here, and if we look at age equals young, we have 3 there that have astigmatism yes. And we have another 6 cases of astigmatism yes on the next page, so that's a total of 12 astigmatism cases. Is that right? 2 out of 4. Where did?
There were 4 young.
Yeah, there was 4.
Astigmatism.
There were 4. Okay, thank you. Where's the young? Here's the 8 young people. That was our, and that was the second thing we were looking at was age young. Of those, we have 4 yes astigmatisms, And of those 4 cases, 2 of them have a recommended lens as a hard lens. So that's where we're getting this value for the next term. If the astigmatism is yes, that was our first branch, so to speak. And now we're our first part of our rule. And the age is young. That restricts us to 4 cases, of which 2 give hard lenses. If astigmatism is yes and pre-presbyopic is, there's 1 out of 4 instances with the same recommendation, and so on. And by the time you get to spectacle prescription equals myop, I'm probably mispronouncing these, but you have 6 instances where your astigmatism is yes and spectacle prescription is myop. Of those, 3 are classified as hard lens recommendations. Clear?
So yeah, we're just looking at how...
It's basically the same thing, except now I'm restricting myself to a subset of the prior set.
So it's like seeing how the variables correlate to each other somewhat?
What do you mean by how the variables correlate? So
like, I'm seeing like astigmatism, age, all that stuff as certain variables and how they pertain to the hard contact lens.
Right. So we first, I mean, our first attribute, I mean, we said our first rule was if astigmatism equals yes.
Right.
And now we're going to an and statement.
Right.
And age is young. Okay? Well, there's 4 for which astigmatism, 4 instances for which astigmatism is yes and the age is young. Of those 4, 2 give a recommendation of 4 hard lenses.
Right. Yeah.
And see how we're trying to build these rules.
Mm-hmm.
And similarly, if astigmatism is yes and our prescription is myop, we now have 6 instances, of which 3 have a recommendation for hard lenses.
Yeah.
And if you look on the right-hand column again, we notice that the largest fraction comes from choosing tear production rate equals normal. So at this point, we're building these rules. So at this point, our current rule stands as follows. If astigmatism is yes, and tear production rate is normal, then we'll have a recommendation of hard lenses. Yeah, Jeremiah.
Question. If you go back to the previous slide and you look at tear production rate reduced, would we, if there were more options for tear reduction, or tear production, would we want to say that if it's reduced, you don't want that in some way?
Well, I mean, we're going to handle that. I mean, you can do something like that, but we're going to really, right now, we're only looking at the case for recommendations for hard lenses. So we're again, this is coming kind of, I mentioned that this is more of a bottom-up approach. Instead of splitting on the attributes per se, we're looking at the final outcomes. What do all these hard lens recommendations have in common? And we're trying to find a rule that points us to hard lens recommendations. Can you kind of see that bottom-up approach coming from the actual classification and building the rule rather than starting at the attribute level and building down to the classification?
So you have the class and now you're finding the attributes.
Right, right. And so are we done? Well, it depends. And I think I mentioned this earlier on. For not if we want to get exact rules to cover everything. And we've only looking at, so far, only hard lenses. So, but we haven't necessarily covered everything. In fact, I think we've covered everything except, there's 4 hard instances. Was that right? I think so. I'd have to go back to the original model. And I think we've covered 3 of those so far. So now, notice we've now eliminated, and this happened on the prior step as well, no longer do we have any of these stigmatism classes or splits here. We also no longer have our age. Or no, what did we, our tier reduction rate. Because there's age right there. So that leaves only age and spectacle prescription terms left to work with. And notice the number keeps shrinking at each stage. The number of possible terms that we're going to add on to the next stage. So now this time we can look at the 3 different ages, young, presbyopic, and whatever. And the spectral prescription. And notice that here we have 2 of the remaining 2 cases covered. Whereas in spectacle prescription equals hypermetrope, equals myope, we have 3 out of 3 covered. Both of those reduce to the same fraction, 1. Which one would we, however, choose? We're going to choose the 3 out of 3, or spectacle prescription equals myope.
I have a question.
Yes?
How can you decide whether an attribute can be disregarded or not? Like if it doesn't, I guess if the data is too inconsistent.
Right. Also, I mean, as you go through this process, you might find out that you don't even need one of the attributes never even comes into play.
Yeah, that's
right?
what I mean.
So maybe it's covered completely, contained within another attribute. So it's repetitive.
Okay.
My name's Katie. I'm great.
All right. Yeah.
I mean, does that?
Yeah.
What would be an example of that?
Well, I'm just thinking of like
I mean, a simple example is. No, that wouldn't work.
Well, back to the weather thing, right? Where it's like
Right.
the wind chill is a combination of attributes, so you disregard the other ones.
Right. Well, that again, that's going to be a decision that you're going to make, and
Isn't that bad?
whether that would be an example of feature reduction, eliminating attribute reduction, because the computation just gets so huge you can't work with everything in a reasonable amount of time. So there you might try to do some combination
Right.
to help out.
Because we're putting stuff into like if-then statements,
Right.
right? So like we don't want a huge if-then, if this, if this, if this, if this, if this.
Exactly.
If this, you know?
I mean, the same thing's going to be true with the decision. I mean, there's a close relation between decision trees and rule-based classifiers in the end, and that this you can write as a decision tree for a rule-based classifier. But they can just grow quite large.
Let's see something.
And how are you going to, I mean, that's where you come in.
Right. It's up to us to decide which
Right.
attributes.
And which algorithm are we going to use? And what's important, and that's why I really emphasize early on in the course the data preparation, early in the beginning. Deciding on attribute selection, cleaning the data, because all of this is going to impact what happens in the end.
Trying out what,
And there's ways to prune some of these trees. Sometimes you get a lot of overlap, and you can go back and clean up some of these rule sets and decision trees. Pruning them. So at the current state, our current rule stands as branching off of 3 if-then statements. If the astigmatism is yes, and the tear production rate is normal, and the spectacle prescription is myope, then the recommendation is hard contact lenses. We're still not done, right? Because we've only covered the hard contact lens instances. We still have the soft contact lens cases to consider. I mean, if we only had hard and soft, you could say, well, we've covered all the hard, so everything else would be soft lenses. But we still have to, that's why I wanted to use a more interesting example than the weather example where we only had 2 classes. We don't, oh, actually, now here's where, yes, so far we're not even done actually with the hard contact lens case. We have to go back and see what's all been covered. We have one remaining instance that we've not covered with this rule to get to a recommendation of hard contact lenses. At this stage, we've pretty much gone through the rules we can possibly go through. So we want to find, how can we find this last instance for hard recommendations? And so what we're going to do, backing up here, we're going to begin the process over again. But before we do, we're going to remove all the instances that we did cover, because otherwise we'd just be repeating the process. So all the instances for hard lens recommendations that we've been able to obtain through our rule so far, we eliminate all of those before we begin a fresh approach. Does that make sense, Pablo? Because otherwise we'd just be in like an infinite loop.
Right, we're looking over the
And
same data.
we'd be looking over the same data. So now we want to strip out the stuff that we've already found and now try to get the last instance. So this time, do I need to go through it in detail like we did last time, going back to the?
Oh, we're good.
Yeah.
Okay. So this time we're going to obtain a new rule,
Okay.
repeating the process that we did last time, except without those instances that we've originally found. And we obtain this new rule: if age is young, astigmatism is yes, and tear production rate is normal, then we recommend hard lenses. Now, I got ahead of myself a little bit ago. Now we're going to repeat the process looking at all the soft lenses. And yet again for none, although by the time you're done with the soft lenses,
To just say,
you can just say everything else would be neither.
Right.
Okay. The method I've talked about is sometimes called the prism method. It generates perfect rules, 100% accuracy, as long as it's doable, given that everything's classified exactly. Basically, you're going to just keep adding a clause to all your rules until you get it right. So I wanted to finish by talking kind of about the characteristics. These are rule-based classifiers. We had decision tree classifiers last time. So we end up with expressions that are very similar to decision trees. A decision tree we can write as a rule. A rule we can end up usually writing as a decision tree. Another similarity between the two, and we'll see how this differs with some other classifiers in a little bit, is essentially create, and where I'm getting this idea of rectilinear partitions of the attributes space, and then assign classes to each partition. If you think of x and y coordinates, if you think of a rule, in a rule-based system, you can say, well, if x is greater than 5, then do this. And if y is less than 2, so if x is greater than 5 and y is less than 2. So that's where that idea of rectilinear attribute partitions comes in. So it fits into one, and then you found a range for the other as well. Difference, the decision trees are sometimes called divide and conquer, or they're a top-down approach. We're starting with the attributes, splitting as we go down, and the rule-based are more starting with your instances and moving up to find rules to get to those instances. Performance-wise, they tend to be comparable. But it's going to depend, again, as with everything, upon the problem at hand. So I'd like to take a little break here. Questions about decision trees or rule-based classifiers? You got it? Drew? Katie? Florida? You're good?
Yes, sir.
Okay. Then we'll move into a completely different type of classifier. These are called nearest neighbor classifiers. And they're going to have slightly different characteristics, or actually quite different characteristics. So something you should be aware of. It's an example of what's called instance-based learning. Some also called lazy learning. And I'll explain why it's called that at the end. The classic example of this is called the k nearest neighbors algorithm. And we're going to go through this algorithm. Basically, there is not really a real training phase. And all we're going to do is we've got our training set, our training examples, and the algorithm's just storing it. It's not going to learn a model. Storing the training set along with the class labels. In the last example, hard contact lenses, soft contact lenses, or not. K is a user-defined parameter, and it's going to be very important in how, in the efficacy of the algorithm. And the basic idea is you're going to select an instance from your test set, a test point. And you're going to measure a distance using some distance measure. Euclidean measure, we talked about similarity measures. I don't know how many lectures ago that was. Hamming distance, and so on. And you're going to measure your distance from your test point to all the instances from your training set. Okay? And you're going to select from those the k nearest neighbors. So it could be the 10 nearest neighbors or the 73 nearest neighbors, whatever your value of k that you selected is. And then you're going to assign a label to your test point by using majority voting from those k nearest neighbors.
What do you mean by that?
Okay, well, how many students are here in Alamosa? There's 9. Okay, I'm maybe the test point, right? And you're going to classify me as either what?
Good or bad?
Good or bad. Okay. So now you're my 9 nearest neighbors, and then there's a whole bunch of other students a lot farther away, right?
Mm-hmm.
And if I chose as my k to be 9. Then you will vote on whether I'm good or bad.
Okay.
That's a setup, right? How many say I'm good?
Joking, right?
4? How many say I'm bad?
I'll be in
4.
5? So you just classified me as bad.
We're sorry, it's nothing personal.
So, I'm just trying to think if I would do that with specific data.
Okay, so with specific data, it's going to hinge on your metric, right? But you've selected the 9 closest neighbors, right?
Okay.
And then Nick here, and then it's just whoever, so if it's a binary decision like that, as long as I chose k to be odd, you're going to classify in one label or the other. In this case, it was binary, it was good or bad.
Okay.
There were 9 of you. 5 of you voted bad, 4 of you voted good. So I'm classified as bad. Simple as that.
Okay.
What if it's an even number? So where it's like 4.
Well, then you chose a bad value for k.
Yeah. Yeah.
Yes.
So if you're doing this with data, it's the attributes of the data points around it that are
Right.
doing the voting?
Right.
Okay.
Well, not the attributes. Well, no, the attributes are determining the closeness,
Okay. But then you're looking at those and
and then looking at the label that you're assigning to the class, the attribute that you're using for decisions.
okay. I got you.
You got it? Florida? Did that make sense? Okay.
Okay.
Moving on.
Good speaking.
So I'm going to talk there. K is a parameter. It's a user adjustable value. And so the parameter selection, the best choice for the K value is going to depend upon the data you're working with. Typically, larger values can reduce noise artifacts, can smooth out the data so it's less noisy. But as it tends to kind of make your class boundaries between your yes and no's, good and bad's, more fuzzy, less distinct. So again, there's always trade-offs here. Sometimes you can use some ad hoc heuristic type methods for choosing your parameter, or what teams I've worked with a lot use are, you're going to actually use some sort of evolutionary algorithm, genetic programming, estimation of distribution algorithm, all these different evolutionary algorithms, which are algorithms based on the principles of evolution, to optimize your K value according to what's called some fitness function, which is typically the performance of the system. So, I think I went through this bottom part. I think that's a repeat.
That was the last slide.
Oh, was that the last slide?
Yeah.
And some typos. Distance measure selection. Well, what measure? Pablo's laughing at the typo. Typing too fast. Is important. If you don't use the correct proximity measure, the correct measure of how you're defining your distance, it can lead to poor predictions. One of the issues there is that the scale of the attributes, how much they vary, is important, because your distance measure might overemphasize some attributes that shouldn't be overemphasized. So you have to look at what your distance measure you're using for the particular problem it is. I don't know what I just said there, but you have to look carefully at what distance measure you're using, see if it's weighting appropriate attributes correctly. So these are issues to consider. Some characteristics, and I'm going to end up talking here about, I said I'd come back to what it is I mean by instance-based learning, because the other rules, the other two algorithms we've looked at for classification, decision trees and rule-based classifiers, work in a much different manner. Instance-based means we're not building a model. Okay? If you think of rule-based classifiers, you're actually creating a model, and then once you get a test instance, a test example, a test point, you just plug those attributes into your model to get your classification directly from the model. Instead, what we're doing is you're looking locally to make our decisions. Literally, according to the distance, we're looking at our nearby neighbors in the example we just looked at. But in general, with instance-based learning, you're actually, if you remembered how we did that, we had to look at the entire training set to calculate those distances for each and every instance in your test set. That's computationally expensive. You haven't created a model where now you just plug it in and the answer gets spit out. Instead, you have to find your k nearest neighbors for your first test instance. Now you have another test instance. You have to repeat that process all over again. The model building is cheap for instance-based learning because there is no model. You're just storing your training set. But using your training set to obtain classifications is expensive. You see the difference there? So with decision trees and rule-based learning, you're spending a lot of time building the basic models. But once those models are built, you can apply them very quickly to different test sets or to your actual real world data. Here, the model building is cheap, but applying the method to your test sets and real world data is very time consuming.
So what would you use this for?
We'll come to that. There are advantages, and they're farther down here. Some other issues, it requires the distance measure. We talked about that. It requires a classification function. We use the example of majority voting. You could come up with a different classification function depending on what kind of classifying we're looking at. You could use a maximum function, minimum function. Here's one good point in favor of K nearest neighbors. Our decision boundaries can be more complex. Okay? Remember in the decision trees and rule-based learning, our decision boundaries were pretty left, right, up, down type rectilinear decision boundaries. Here they can be a lot more curvy, a lot more complex. There are other ways to get there, but
yeah.
Another downside, the decision boundaries can be variable, and it's going to depend on the parameters K and your distance measure, your classification function. So, in contrast, we talked about rule-based classifiers, decision tree classifiers are sometimes called eager learners versus lazy learners.
No.
The first two approaches we looked at, decision trees and rule-based classifiers, create the global model of your entire input space. Long training time to develop model, short time classifying test points. So we talked about that. But again, decision tree and rule-based classifiers, at least those two, tend to be restricted to fairly simple decision boundaries. If your boundaries become really complex, now you're going to be using a lot more steps to try to build the model using rectilinear approaches and building a much more complex model than otherwise would happen. So I think this is a good place to stop with a preview of
Phase theorem.
Wednesday's discussion. Well, we're going to move into a few other approaches for classification, starting off on Wednesday with Bayesian classifiers. It's our first algorithm where we're going to start actually using probability and statistics. And I'm not going to go into that today.